but you'll need you'll handle for them to hear.
And for the video.
Yeah.
Oh, wait.
That one's for the video, and this one's for everybody here.
Oh, okay, good to know. All right. So
Or you can switch on. You got to switch on.
switch off.
Yep.
And we're on. All right. So my name is Phoenix, and my project was the robotic arm. My poster is back there. You can actually see it in the back corner. So what was the problem that I found? Well, as Mr. Smith said, I was born with a limb difference, so I'm missing some fingers. So something that's always been kind of interesting to me is prosthetics. However, there's a lot of barriers to that. The first one being that mechanical prosthetics, which are simply body powered, so no interfacing with a person, no motors, nothing like that, can cost anywhere from $8,000 to $20,000 or more. So you're dropping the equivalent of a car. And myoelectric prosthetics, which are ones that actually sense some sort of body input and then translate it into some sort of motor movement, can cost anywhere from $20,000 to well over $100,000. That's a lot of money. And another big issue is that this is actually something JC mentioned with her presentation. We did not organize this. There is a lack of individual customization in the world of accessibility devices. For prosthetics in particular, often the device isn't designed for you. You have to suit the device to even get fitted. And obviously, that's a problem. And I only discovered this because I am not eligible for basically anything that's on the market, just by pure chance. Because most things that are on the market are for people who have been accidents, like work-related accidents, and so they got an amputation. The project, this is a slightly older version, the one on screen with the dials. That arm in total cost $101, which is significantly less than $8,000. And the other bonus, because my intent with the skills that I gained from this project is to work on prosthetics, is that you can actually individually customize this sort of stuff for whoever needs it, instead of sort of having just the hand equipped and then a sleeve that you stick onto the arm and then you say, all right, I hope it fits. Like I said, I've been interested in prosthetics for quite a while. So I first started working on them in 8th grade, actually, just for fun during COVID lockdown. I had time to kill. So I ended up working on that, and I was in the middle school engineering program, and we actually got the opportunity that December to choose our own project. So I said, I'm gonna keep working on prosthetics. And so I ended up making a sort of partial hand instead of fingers, which is what's in the first picture. It was semi-functional, proof of concept, basically. And so come sophomore year of high school, when I was in the mechanical engineering class, our teacher again said, hey, you can choose the project you want to do. And so I said, I'm interested in working on prosthetics. And another student, actually, his name's Aaron Messner, he was the class of 24, so he graduated last year. He did his capstone presentation, actually, decided to join the project with me. And so we decided that our project was going to be prosthetics for the year. We had no idea how to accomplish that at all. Neither of us had any experience with any sort of Arduino use, no experience with anything that we needed, basically. So our teacher, Mr. Ng, told us, hey, let's try to get you guys a little bit of experience. I have some students from Biola who recently made a robotic arm. Would you like to have the diagram for that and some of the code and see if you can assemble it? And we went, sure, that should only take a semester. We can just get this done and we'll have experience for second semester. It did not take a semester. But we eventually, after a lot of trial and error, a lot, and learning a lot of things, such as what an Arduino is, the fact that it is not compatible with a Raspberry Pi. We learned that after 3 months of zero progress. And just general design things, we finally got it actually working. And the Biola students actually had a control box, so we ended up designing one of our own because we were not given those files. And it was about this time in the project that Aaron left the project. This was near the very end of sophomore year. And he went and he joined an escape room project, I believe, if my memory serves me. I continued on this project and I worked on designing another claw for the arm. Because the one that we had bought previously was like 14 bucks for the claw and the motor. A motor that you can get for $2. And that's pretty impractical. So I ended up just designing something that you could 3D print. And by the end of the year, May, so basically around this time, 2 years ago, we had it fully functional. And this is a video from early on in development. As you can tell, considering the control box is not intact, this was an early sort of proof of concept that we had actually gotten it moving. Enter junior year. Again, I had Mr. Ng, and again he said, hey, you can choose what project you want to do. So I went back to the same project. And this picture is from May. I actually finished this design a bit earlier, probably around February, I think, where I just switched from potentiometers to flex sensors. Because a dial, you have to twist, you can only do so much of that. But a flex sensor is much closer to what I was aiming to do, which is some sort of interfacing with the actual human body. That's what these rings are for. This model actually is upstairs on the table. Is you could put the rings on, and when you bend your fingers, it bends the sensors, and so the arm moves. Near the end of junior year, I decided to start converting to EMGs. EMG stands for electromyogram. An electromyogram is a board that senses your muscle movements because your muscle moves by electricity. Electrical pulses cause the fibers to contract, and that's how you get any sort of movement. And that electricity can be picked up by electrodes, which are what I have strapped to my arm right now. And so the end of junior year largely consisted of just kind of figuring out what the heck these boards are, because they were at a much higher difficulty range than what I had previously been working on. After senior year, I declared fully converting these to EMGs and switching my boards from Arduinos to ESPs. More on that later. I declared that as my capstone project. So, early senior year, started working. First I started using a Mega, which is the board on the right, which is a lot nicer than ESPs, which are shown in this image. An ESP board is a board which has what's essentially Bluetooth capabilities. Well, they do actually have Bluetooth and Wi-Fi, but they also have this neat little thing called ESP Now, in which you can connect two ESP boards directly to each other and they can communicate wirelessly. The ESP boards have basically been my biggest challenge for the entire project because they are very finicky. They're very advanced boards, so you can do a lot with them. The consequence being you have to do a lot with them. At this point in the project, for example, I had gotten it working with the Arduino Mega, and it was working pretty well. And so I said, all right, let's switch to ESPs. And then suddenly everything was jittering a lot, just constant twitching, constant crosstalk between the boards. I would use one board and it would move another motor. And I'm like, you're not supposed to do that. So I figured, my first course of action was to shield some wires, which is what this is. You'll actually find these in your walls if you decide to remodel your house, because they're used to prevent electrical fields from being formed by the wires and that causing interference. Unfortunately, that didn't work because the issue, it turns out, is actually in the boards themselves. They put off a pretty strong field when you use them because you have to feed them 18 volts. So I spoke to Mr. Smith about this, and he said that if I wanted to continue down this route, the next course of action would probably be to wrap them with copper tape, wrap them with electrical tape, and hopefully that would stop them from communicating with each other. I decided to pivot instead because that wasn't a guarantee, and so I was like, gonna keep that knowledge on the back shelf, but I'm gonna do something else. This video is from when I had it hooked up to the Mega, which was the board that's actually forgiving and does not cause a bunch of finicky issues. And this is how the EMGs are supposed to work when you hook them up. It was around this point in the year where, fun fact, Oaks has a mentorship program for some Capstone students. It's pretty small, and we typically are supposed to have a mentorship night, but apparently we're not doing that tonight, so talking about it here. And it's run by Gazim Gashi. And he's from Sweden. He's connected with a whole bunch of industry professionals. So the point of the mentorship program is that we can talk to people outside of Oaks. He connected me with Mr. Medney, who I showed my presentation to. I had basically shown him what I had until this point. We spoke, he gave me some feedback on my presentation. He also gave me feedback on the design process, and he told me I was on the right track of iterating, constantly, changing one thing, realizing that was a mistake, backtracking, it stops working, fixing that, moving forward, it stops working again, and just continuously just iterating over and over again. And then this is second semester of this year. I broke quite a few things by accident. I think I shorted an EMG around the same time that my ESP boards decided to stop working, because a part of them being super finicky devices is that they're super finicky and they sometimes just randomly die. So I decided, well, new EMGs came in the mail, that I would switch to flex sensors just as to see if I could get them working. I had both EMGs and flex sensors attached to the ESP boards. Unfortunately, EMGs put in 18 volts. Flex sensors use 3. Turns out the ESPs do not like that. Every time I would plug in both at the same time, it would just completely white out, would get no data. Had no idea why. So I asked Mr. Smith, what am I supposed to do? He directed me to Dr. Moon, who's our resident electrical engineer. And Dr. Moon told me, try making a voltage splitter to drop that 18 volts down to 3 volts so that you can feed the ESP boards 2 voltages of the same value at the same time. I said, okay. I started working on that. And then while I was working on that, I decided, okay, I'm gonna switch to just flex sensors just to test it out. And I realized there was a problem with that. The baseline oscillates up and down very slightly, very consistently, and very slowly, which is a big problem because sensors give you back a value, say for a flex sensor 200 to 400. And so in your code, you say when it's 200, your servo should be at this angle. When it's 400, your servo should be at this angle. If your range starts drifting upwards, your motor starts moving because it thinks it's getting a reading. It is not getting a reading. I did not want it to move, and it started moving. And this is another issue that, like earlier with shielding the boards, that I'm fairly certain, given maybe a math textbook, maybe a computer science textbook, and quite a bit of time I could hammer out in the code, because it oscillated so consistently, I could find a way to smooth that out and then map the readings. But I basically said, at this point, that sounds like a lot of computer science reading, and I'm working on APs, and so I'm gonna switch it back, and I'm just gonna go back to using ESPs, or EMGs, because my EMGs had arrived in the mail at this point. And so I ended up hooking those back up. The model is as it is right now. This picture was taken, I think, yesterday. So it's very up to date. It works mostly like it did in the video I showed before. It's still very finicky because the ESP boards are very finicky by nature. It's quite annoying. But second semester, if you can't tell, is a little bit more sparse than first semester is. That's because, as Mr. Smith spoke about at the senior awards night last night, when you let seniors organize their own projects, things go awry a little bit. So second semester I started facing a lot of time crunch. I didn't really factor in APs into my schedule. Senioritis caught up with me finally, unfortunately. And was one of my biggest takeaways from the project as it is now, considering my project is a little different from a lot of these capstone projects, in that mine was a lot less focused on here's the problem, here's the solution, and a lot more research focused, because I was just trying to accumulate skills that I can eventually apply later to prosthetic work. And so I learned a lot, especially considering this capstone spanned over 3 years. I was 15 when I started. Biggest one being perseverance, because I was 15 when I started. You know, it's been a long journey. And I also had to learn how to combat scope creep, which was another big problem that I faced senior year, especially second semester. I would have a new problem and I would say, oh, I think I can fix this. And I'd start trying to fix it, and that would just snowball and create 5 more problems, like a hydra. You can't kill it. And so I had to eventually speak to Miss Rubin and be like, I have no idea what I'm doing. This has gotten a little out of hand. And she told me, just back off, reduce the scale of your project a little bit. And you know, that kind of sucks, because when you go into it, you think, oh, I'm gonna get this working perfectly. That was important to learn, is you cannot always get it working perfectly. Time management became really important, especially senior year when I wasn't in class and had dedicated class time to work on it. Having to set up a space in Miss Rubin's room, claim the back desk, and just say, okay, I'm gonna be here on these days, I'm gonna put these hours in. I also had to communicate with Gazim a lot and text him, because he, unfortunately, just like the real world, did not text me, hey, when we'd like to meet. No, I had to actually be the first one to text him. And that took a little bit of getting used to, because something that I don't think we realize in high school is that our teachers do a lot to keep in contact with us. The teacher will email you, hey, yes, I see you're missing this, or hey, you need to make up this test, will you schedule it with me? That does not happen in the real world, unfortunately. I also learned how to use some resources like AI and even, you know, Google, considering that for the projects, part of Capstone is that we choose our own project, so we don't have a teacher and a curriculum that says, oh, here's the first part, here's how you do it, here's the second part, here's how you do it. You have to figure out how to do that on your own. And so I got pretty good at using Google and figuring out which search terms to put in. Of, here's my device, here's my problem. Let's hope that there's some 14-year-old forum page that just happens to have the solution. I also just, in general, learned a lot about how to use a bunch of different devices and a bunch of properties of electronics, because, like I said, starting the project, I knew nothing. And I still kind of know nothing, but I know more than I did then. And most importantly, as I mentioned earlier, is just learning to accept failure sometimes, because it doesn't always go the way you plan it to, which is unfortunate, but that's just how life works. And that's something that I kind of had to come to peace with, especially as the student I am. It's very, very like, I gotta get an A, gotta get that 4.0, gotta finish everything, every deadline right on time. Unfortunately, that's not something that you can do. And I ended up learning that over and over and over again during the course of this project. Thank you.